Hello everyone, my name is Arnab Bose. I work in Cornell University with Professor Robert Berman and Professor Dan Rolfe. Today I'll talk about the effect of carrier lifetime strain and Dirac Nodal lines on high spin Hall conductivity of epitaxial iridium oxide thin films. First, I'll start with the motivation for iridium oxide. Dirac semimetals are the 3D analog of graphene, where crystal and time reversal symmetries are preserved. In addition, if material has non-symmetric symmetry, then conduction and valence band may touch in multiple places in momentum space, forming Dirac nodal lines. So it was predicted that rutile crystals will have this additional non-symmetric symmetry. Recently, this theory work predicts the existence of Dirac nodal lines in various rutile oxides. And also, it predicts that this DNL will contribute to spin Berry curvature, leading crystal direction dependent spin Hall conductivity, as tabulated here. Recently, our collaborators have shown the experimental evidence of Dirac nodal lines in MB grown thin film iridium oxide uh, down to 5 nanometers by APS measurement. Here we can see the locus of Dirac nodes as we go from x to m direction in momentum space. The experimental observation is quite consistent with the theoretical prediction. We have grown single crystal iridium oxide by MB on single crystal 001 and 110 titanium oxide substrate. 001 iridium oxide grows centrosymmetrically with uniform strain, whereas 110 iridium oxide grows with asymmetric strain in two different directions, which leads uh, in asymmetry in resistivity, as shown here with red and blue curve. This asymmetric strain also breaks the non-symmetric symmetry. So since the non-symmetric symmetry is broken, there is a gap opening in Dirac nodal lines, which is zoomed here. Whereas for 001 plane, Dirac nodal lines are still preserved. These are the DFT calculations as shown in this paper. Along with that, we also find that under coordinated oxygen atom density is very high on 001 surface of iridium oxide compared to 110 surface. These under coordinated oxygen atoms can react with the permalloy, decreasing the spin torque efficiency. So we needed to put 1 nanometer of passivating iridium spacer. Hence, we measured all these four set of devices. TM images are also shown here. To verify this, we have done yields measurement. Here we show yields study of 001 iridium oxide and permalloy bilayer. Uh, we can clearly see there is a significant overlap of normalized oxygen and iron atom density, which clearly indicates there is a significant oxidation of iron atoms near the interface. When we inserted 1 nanometer iridium, we don't see any evidence of oxidation. In comparison for 110 plane, there is some oxidation, but that is quite less compared to 001 plane. We have performed standard STA-FMR spin torque ferromagnetic resonance measurement to quantify spin orbit torques. In brief, micro F current is passed in the system and DC voltage is measured in presence of external magnetic field. A radio frequency current produces spin torque on magnet which undergoes small oscillation. This oscillating resistance in magnet with oscillating current produces DC voltage spectrum. Here you can compare DC voltage spectrum for 001 and two different directions of 110 plane. Symmetry component gives us information about the damping like torque efficiency generating from spin Hall effect, whereas the antisymmetry component gives us the field like torque efficiencies. We define spin torque efficiency with this expression, and if we have strong um, field like spin orbit torques, then we can get damping like torque and field like torque efficiencies from this expression. The inverse of spin torque efficiency is plotted against the inverse of magnet thickness, which goes like a straight line. From this expression, it is evident that inverse of intercept will give us the damping like torque efficiency, whereas from the slope we'll get the information about the field like torque efficiency. Here we can compare the damping like torque and field like torque efficiencies for 001 and two different directions of 110 planes, which clearly shows the anisotropy in spin Hall conductivity and damping like torque efficiencies. But interestingly, when 1 nanometer iridium is inserted, damping like torque increases by factor of 3 for 001 plane. Whereas for 110 plane, the damping like torque efficiency goes down by factor of 2. That indicates there is a significant attenuation of spin current through 1 nanometer of iridium spacer that gives us the spin attenuation length of iridium around 1 nanometer, which is consistent with this experiment, with recent experimental work. Even if we have that amount of significant amount of spin attenuation through iridium spacer, still there is a giant enhancement of damping electron efficiency for 001 plane, indicating that the interface has been improved with the iridium spacer. Here we show the temperature dependence of spin orbit torques. Both damping like torque and field like torque increases strongly as temperature is decreased for 001 plane, whereas for 110 plane, uh, damping like torque decreases for both the directions and field like torque doesn't change too much. From these damping like torque efficiencies, we can get the effective spin Hall conductivity. By the way, this damping like torque efficiency is the lower bound of actual spin Hall angle, and this effective spin Hall conductivity is also lower bound of actual spin Hall conductivity. From this figure, we can clearly see that spin Hall conductivity for 110 plane along the low resistive direction is almost independent of the electrical conductivity as shown with the blue color. Whereas, so this clearly indicates that this direction belongs to the clean metal regime limit, whereas for 001 plane, the spin Hall conductivity is strongly and linearly increasing with the electrical conductivity, indicating this belongs to the dirty metal regime. Okay, so in the clean metal regime, we also notice that there is a significant anisotropy in spin Hall conductivity along two different directions of 110 plane, which indicates the strain-induced modulation of spin Hall effect, whereas there is a drastic and huge enhancement of spin Hall conductivity for 001 plane compared to 110 plane. That is correlated with the Dirac Nodal lines present in 001 planes. Here we can compare iridium oxide with other members of iridates family. So compared to strontium iridate, iridium oxide has better connectivity in iridium O6 network and increased PD hybridization and broader T2G conduction band, hence lower electron correlation. So iridium oxide is much better, has much better metal-like behavior compared to strontium iridates. Recently, it is experimentally shown that both strontium iridate and strontium ruthenate have a high spin Hall angle and spin Hall conductivity in orthorhombic phase, and this spin Hall angle actually attributed to the degree of tilt present in the system. And this paper also shows that uh, this also shows that if the I mean to have such high spin Hall conductivity, you must need tilt in the system, and also the T2G band has to be small. But compared to that, for iridium oxide, we don't need any kind of tilt to get spin Hall conductivity, and it is present in the. It shows even if iridium oxide has better metallic conduction and broadened T2G conduction band. So these are the advantage. In addition, So degree of tilt can significantly influence spinal conductivity for the strontium ruthenate or and strontium iridates. For example, even the sign can also change. So this kind of tilt can be uncontrolled sometimes. Iridium oxide has better. Uh, Iridium oxide has advantage because it doesn't require this kind of tilt to have spinal conductivity. So finally, we summarize the anisotropy of spinal conductivity between 001 and 11 O planes. This large anisotropy is attributed to the effect of Dirac Nodal line present in 001 plane, and the anisotropy in spinal conductivity along various directions of 11 O plane is attributed to the gapped Dirac Nodal lines due to strain effect. Here we can compare the spinal conductivity of iridium oxide uh, with other standard platinum-based alloys and strontium ruthenates and strontium iridates. One takeaway message is that already 001 plane shows very high spinal conductivity, but still it is in dirty metal regime. So if we can get better and less defective 001 iridium oxide plane, then we can get very high spinal conductivity, which will saturate at very high number. And here we compare the data for iridium oxide with iridium uh, spacer layer. So actual spinal conductivity of bare iridium oxide would be much higher than the conductivity shown in this plot. So this large enhancement in spinal conductivity is order of magnitude higher than the theoretical prediction. So this will definitely motivate the theoretical researchers. Uh, Thank you for your attention.